Okay, welcome to today's lecture. We're going to start chapter 14. We're going to talk about multivariable functions. So this is our objective. Multivariable function. Well, first of all, what is a function? Recall that.
Professor, the camera's out of focus.
So recall that in elementary calculus, in algebra, we learned that y equals to f of x is defined as a function. We have a function. It means that it acts like a machine. You have a machine like f. You have some input values like x. And then this machine changes those x values and gives you some outputs like f of x or y. So these are your inputs, and these are your outputs. Very well. So we say that all the acceptable input values are the domain. Domain is the set of all acceptable x values. It means that we're not allowed to plug in anything that we like into this function. This function might be able to change some of x values, not all of them. That depends on this machine. We denote the domain by domain of f equals to d sub f equals to the set of. So our domain is actually a set. Set denoted by curly brackets, the set of all x values such that this function actually can take those x values and set them equals to these output values or just y values. So f of x is defined. This is what we learned in algebra, in pre-calculus, in elementary calculus. So remember that the domain is the set of all x values. So this is the set of all x values. This vertical line, you read it as such that, with condition that f of x is defined. Well, this function takes on x values on the real line. X values. And maps them to y values. Real line. These are y values. This is your function. This is your machine. So your free variables are x values. Now I expect you to ask, what if I have two free variables? What if I have three free variables? What if I have n free variables? How do I define the domain of those functions? So here's a question. These are the types of questions that you should be asking. Question. What if we have more than one free variable? Here you have just one free variable, your x values. You can plug in different values for your x, and the acceptable ones actually define the domain of your function. What if you have more than one free variables? There we define a function with two free variables, three free variables, and so on. Then we define the domain for each of them separately. There you go. Definition of function with two free variables. Function with two. When we are saying variables, we are referring to free variables. So if you need more clarification, you can always write free variables. It means that you can freely choose those values for those variables and plug them in to check to see if the function is defined for those values. So a function in two free variables is defined as f of x comma y. You're allowed to plug in freely values for x and for y. So this is a machine. It takes on ordered pairs, x and y, make some changes, and give you an output. So this is your machine. This is your f. Now you plug in x and y values into this machine. It takes two values and it gives you back some output values that we call z. Z is equal to f of x and y. These are your outputs. Very good. So we have a machine. It takes on ordered pairs, x and y's, and it gives you some numbers like z. So remember that here you have ordered pairs, x comma y. So when you want to represent this function, you have to have x, y plane. This is x-axis, this is a y-axis. It takes on some points in x and y, and it maps them to z-axis, z values. These are real values. This is your function. Your function takes points and map them to real values. It takes 2-dimension and map 2-dimension into 1 dimension. X and Y's, they are all located here. So the domain of this function is defined as the set of all ordered pairs, all points like X and Y, such that this guy is actually defined for those points. F of X and Y is defined. If it's not defined, it means that those points, they don't belong to the domain. Those are just right down here. And all of Z values form the range of your function. This function takes ordered pairs like X and Y and maps them to real numbers like Z. So if we have a function in three free variables, note that if we have a function in three variables, we denote it this way: f of x, comma y, comma z. The domain of this function includes all triples x, comma y, comma z, such that this output is actually defined. Your machine can take on those values and actually give you a real number as the output. So the set of all triples x, y, and z, such that this output is defined. Example. Suppose you have this multivariable function. Let f of x and y be equal to square root of x plus y plus 1 divided by x minus 1. First of all, what is the domain of this function? And second of all, what is f of 3 and 2? What if I plug in 3 and 2 for this function? As you can see, this function has two free variables. And then it has something on the numerator, it has something on the denominator. We are going back to elementary calculus, what we learned in elementary calculus about the domain of a rational function. Recall that. For a radical expression, if we have square root of a quantity like u of x, whatever it is, to find the domain, we have to take this u of x and set it greater than equal to 0. And also recall that if you have Vx divided by Tx as a rational expression, the denominator cannot be 0. T of x cannot be 0. This is what we learned in algebra. We're going to apply what we learned in algebra here to this function. So first of all, let us deal with the numerator. Our numerator is a radical. So since it's a radical, the quantity inside the radical cannot be a negative number. So x plus y plus 1 must be greater than equal to 0. In algebra, we learned that this can be solved as y greater than equals to negative x minus 1. This is an inequality. Inequality in the plane. We can easily graph this. Take a look at your denominator. Your denominator cannot be 0. The denominator, x minus 1, cannot be 0. It means that my x cannot be equal to 1. So far we have two results. The first result is an inequality, and the second result says, hey, x cannot be equal to 1. Let us graph this to visualize what's going on here. So let us graph this inequality, x-axis, y-axis. Remember that here you have a function in two variables. The domain is part of the plane. Okay, perfect. Let us graph this guy. And here, okay, this is negative 1. And then, so if I plug in 0 as the checkpoint, 0 is greater than equals to negative 1. So this part of the inequality on top of it is going to be part of the solution. This is our inequality. At the same time, it says x cannot be equal to 1. It means that we have to exclude this line. Exclude x equals to 1. X equals to 1 is actually a line. So we have to exclude this line. So we're going to use dotted line to show that you're excluding this. So our domain is actually this part, and this dotted line is excluded. This is your domain. What is f of 3 and 2? Your x is equal to 3, and your y is equal to 2. So we have a nice formula here. Let's just plug that in. We have square root of 3 plus 2 plus 1 divided by x minus 1, 3 minus 1, because square root of 6 divided by 2. This is actually your output value. Or z. So this is how we visualize the domain. How do we officially write down the domain of this function? The domain of this function can be written this way. Let me erase this part of the board. We're going to use the set notation. The domain of function f is equal to the set of all ordered pairs x comma y, such that with the condition that those x and y actually satisfies these two conditions. Y is greater than, equals to, minus x minus 1, and x is not 1. So officially, we write it this way, and visually, we visualize it this way. Okay, let us go over another example. Let us make it more interesting. So suppose you have a new function. F of x and y is defined as you have natural log x times natural log of y squared minus x. What is the domain of this function? So again, we are getting back to what we learned in algebra, elementary calculus, pre-calculus. Recall. When we have log function, natural log, then you have ln of u of x. If you have ln of a quantity, this quantity must be positive. It must be greater than 0. Otherwise, if it's negative or if it's equal to 0 and you plug that into a calculator, you get an error. Otherwise, we get an error. So ln of a quantity, this quantity must be positive. So now that you have a function in two variables, it doesn't matter. This quantity must be positive. So since we have natural log, the quantity, what is the quantity? Y squared minus x must be greater than 0. Okay, y squared minus x must be positive. Well, so if you want to write down the domain, it's easy. You can say that, hey, the domain of this function is equal to the set of all ordered pairs x and y such that y squared minus x is positive. But how do you visualize that? What's the domain like? Which part of the plane is the domain? To graph the domain, we have y squared minus x greater than 0. But what is y squared equals to x? This is your graph. You have x-axis, you have y-axis, and this is just this graph here. This is y squared equals to x. Well, this guy says y squared minus x is always positive, or y squared is always greater than x. What's the meaning of that? It means that you shade left-hand side You can plug in values for y and x, or you can just use some random numbers, or you can just solve this. And since it is absolutely greater than 0, we have to exclude the graph itself. So this is the domain of this function. This is the domain. All these red region is going to be the domain of this function. Another square root function. Now, suppose you have function g of x and y, equals to square root of, here we have 9 minus x squared minus y squared. What is the domain? Perfect. So what do we have here? Remember that we have square roots. Again, recall that. Then you have square root. If you have square root of a quantity, this quantity must be greater than or equal to 0. Greater than or equal to. All of those values are acceptable. Even 0 is acceptable. Why is that? Because you know that square root of 0 is equal to 0. We're happy about that. We don't have any problem with 0. So let's take a look at this. We have the quantity, which is 9 minus x squared minus y squared greater than or equal to 0. Let's rearrange this guy. If we rearrange this, it means that we are taking these two and write them on the other side. Or we can write x squared plus y squared less than equals to 9. Or x squared plus y squared is less than equals to 3 squared. What is this? It's actually a circle with all points inside that circle. It's like a disk. So here you have x minus L squared plus y minus h squared less than equals to r squared. If you graph this, the graph is like this. You have x-axis, you have your y-axis, and then here you have radius 3. 1, 2, 3, 1, 2, 3, 1, 2, 3. And this is your circle and all the points inside that circle. You have a disk. This is the domain of this function. So we can use set notation to represent the domain this way. The domain of function g is equal to the set of all points, all x and y's, x, comma, y, such that x squared plus y squared is less than equals to 9. We are visualizing the domain. We're also writing the domain in set notation.